Hello everyone, I'm Santoshni Sekar from Multicore representing the X26 team. On the agenda, first we will have a quick look at the advantages of VVC over HEVC and then a brief introduction to X266 and its design philosophy. In detail, we will take a look at the architecture of X266 and then quickly we will look at the features implemented in the first version of X266 and also how parallelism impacts X266 so far. After that, we will see the next steps planned for X266. As we all know, VVC as a standard was ratified this year in the month of July. I'm not going to dwell in detail into the features of VVC as many sessions have already covered them in detail. The main advantage of VVC over HEVC is that it provides twice the coding efficiency as that of HEVC. That is, for similar visual quality, on an average, it can provide up to 50% bitrate savings. Or in other words, at similar bitrate, it provides significant improvement in the visual quality over HEVC. In addition to many new tools or features introduced for traditional 2D videos, VVC has many advanced tools specifically to address 360-degree videos or online games, video streaming of esports, and so on. Now let's move on to have a brief introduction to X266. X266 is a VVC compliant encoder. Soon we will make it publicly available under GPL v2 licensing terms. X266 is similar to X265 in the sense that it's an application library combination software with all the required API functions to make the application library communication provided. When compared to VTM, which is the reference software of VVC, X266 will be a high-performing VVC encoder in terms of speed, maintaining similar quality of VTM. Another important aspect of X266 is that almost all features will be exposed to the end user in the form of command line options or API functions for them to play with to get desired speed and compression efficiency trade-off. In addition to this, there will also be predefined presets, which is actually a full package of better trade-off options. For example, preset ultra fast provides an high speed encode, whereas preset very slow provides a high compression encode. Now let's look at some of the major criteria that we considered while designing the architecture of X266. The first and foremost important criterion is that X266 should be a high-performing VVC encoder. When we say high-performing encoder, it not only means high speed but also means without loss in coding efficiency. The encoder should be able to optimally make use of the available platform's architecture. Depending on the capacity of the available resource, it should be able to scale up or scale down. Apart from these performance-related criteria, another criterion to consider is the flexibility of the architecture. X266 should be able to run as a cloud entity or as a standalone application on your local machine. It should also accept real-time video streaming or encode a file-based video input. Like discussed earlier, it should also provide good quality and speed trade-off options in the form of presets. Other than this, all the APIs provided should provide simple integration with a variety of applications like broadcasting or video conferencing or cloud gaming and so on. The architecture of X266 is similar to X265's architecture. Some of the basic API functions in X266 are listed down here. The encoder open API, as the name suggests, it simply creates a handle to the encoder and sends it out to the application. The encoder encode API receives the encoder handle that was created using the encoder open API and also pointed to the input picture and output picture. The library does the encoding and sends out the compressed picture through this API. The other two API functions, encoder close and encoder stats, it sends out the encoder close and the encoder stats frees up all the internal memory that was created during the encode and sends out the encoder statistics collected during the encode respectively. Now let's look at the architecture of X266 in detail. The left side shows the application and the right side represents the library as such. The application runs on a separate thread called the API thread, and there is a separate thread that keeps reading the input video and copies the frames into a fixed buffer that can be reused. The API thread invokes the encoder open API function to create an encoder handle. Through another API function, pictures are read from the previously read buffer. From here, the preprocessor module, which is running on a separate thread, receives the pictures and copies them to an internal buffer after converting it to an internal compatible structure. The preprocessor module does a lot of preprocessing, starting from bit depth conversion or noise removal or even chroma subsampling. The most important task of the preprocessor module is to do slice type decision, B-frame placement, or scene cut detection. In addition, it can also do complexity analysis like adaptive quantization or the CUC offset computation. Internally, the preprocessor module copies the slice type decided picture to an internal buffer in encode order. An API function also sends the decided slice type to the external application. This entire preprocessor module can be used as a separate entity because there is an API function to send the input pictures to the preprocessor module and another API to send the preprocessed frame to the outside application. Once the preprocessing is done for a frame and copied to the internal buffer, encoder encode API is triggered. From here, the control is sent to the frame encoder thread. All the frame level operations are performed by the frame encoder thread. Like for example, the rate control or the QP optimizations are done by frame encoder thread. Based on the number of tiles in a frame, the number of tile threads are decided. All tile level operations are done by the tile encoder. Apart from these, we also have a pool of threads called the worker threads. These worker threads are responsible for all major work like the mode decision, transform quantization, or entropic coding. Once the main encoding is done, the post-processing or the in-loop filter is handled by another separate thread called the filter thread. Filter thread is similar to the frame encoder thread because it also has its own set of tile threads. And these tile threads have access to the pool of worker threads. Once again at row level, these worker threads does the in-loop filtering operations. After the in-loop filter is done, the statistics like the rate control statistics required and the encoder statistics are updated. We just saw the overall architecture of X266. Now I will go over the improvements that we have done in X266 compared to X265. Like I said before, the preprocessor module is handled by a separate thread and it has API functions to send in or send out any form of preprocessing information like the slice data or rate control information. This enables us to leverage encode information from GPU and send it to the preprocessor module through the API functions provided. This structure allows the preprocessor module to act as a separate entity so that we can either skip the slice type decision or send the preprocessing data to an outside application. It also gives us the flexibility to add ROI API functions. The other main improvement that we have done in X266 is that we have improved the level of parallelism. In X265, we have only frame threads and WPP threads. Even though there is slice level parallelism in X265, those are still handled by the frame threads. But in X266, on top of frame threads and WPP threads, we also have separate set of threads to handle at tile level. Tile threads become important in X266 because VVC has new advanced tools for 360-degree videos where tiles are important for encoding. With the increased complexity of the in-loop filters, we have decoupled the Quebec engine and the loop filters so that both the complex modules can run on separate thread. The first version of X266 has only intra features. In this version, we have implemented all directional modes including the wide angle prediction. Also, the support for multi-type partition is added. And next, we have also implemented frame level parallelism and WPP. As of now, we support only single tile encode. As far as the GOP structure goes, we have fixed GOP support with constant QP. The support for adaptive B-frame placement will be added in the future. And as of now, the assembly level optimizations are done for x86 based architectures for even complex algorithms like TCT and IDCT. We will continue to add more assembly level optimizations. Here is a snapshot of CPU utilization for a test run on Intel Xeon 6148 server. The top screenshot is for an encode run with single frame thread and WPP disabled, and the bottom screenshot is for an encode run with 9 parallel frame threads and 17 WPP rows. It is evident from here that frame parallelism and WPP is able to almost make use of more than 3/4 of the available threads. From this, we can even imagine how the utilization will improve when we had support for multi-tiles. The plans that we have for the upcoming versions of X266 are that we will add more and more VVC coding tools to improve compression efficiency. We will also add efficient rate control algorithms like the ABR and the VBD. Support for adaptive quantization techniques and CU3 will also be added in the upcoming versions. From full motion search to efficient hex motion search algorithm, similar motion search algorithms will also be implemented. We will also be adding intelligent scene cut detection algorithms, and we will continue to add more and more ASM optimizations. To summarize, we had a quick comparison of VVC and HEVC, and then we got introduced to X266 and its design or the architecture in detail. We also looked at the first version of X266 and what will be the next steps of X266 were also discussed. Thanks for listening to me. We hope to make X266 as popular as X265 to proliferate open source encoding. For more queries on X266, please reach out to us to the email ID provided here. Thank you.